Welcome. This presentation summarizes the contents of a paper published and presented at the EXOBA conference in Athens on 13th October 2022. The paper is entitled Advances in Process Simulation of Agglomeration in Precipitation, written by myself with John McVieters and Daniel Menche as the co-authors. Presentation is essentially the same presentation with the same slides as given for a live audience at the conference in Athens. It has been re-recorded for video quality purposes and has been split into two videos because of its length. My name is David-Rijkeboer. I'm from the Netherlands. I have more than 40 years experience in the alumina industry. As a Billiton employee, I have worked at Worsley, Organish, in alumina R&D, and in the Billiton Central Office in The Hague at that time. Since 2004, I'm an independent consultant to the alumina industry with my company, René. I have worked closely with the SysCAD experts at Kernels over the past number of years on developing ongoing improvements in state-of-the-art simulation of the bioprocess. This is a joint René SysCAD presentation. It covers three items: new agglomeration kernel, calibration of a precipitation circuit model, rate equations for growth, nucleation, and agglomeration. As mentioned, this presentation has been split into two videos. Part 1, which is the current video that you are watching now, deals with the new agglomeration kernel. Part 2 continues with calibration of a precipitation circuit model and with a discussion on some fundamental aspects of the mentioned rate equations. I start with two observations. The first one concerns agglomeration. Agglomeration is strongly dependent on the hydrodynamic conditions within a precipitator. These hydrodynamic conditions differ between the types of tanks and between the various locations within a tank. Therefore, the particle interactions cannot simply be captured by one rigid laboratory-developed agglomeration kernel. We need a pragmatic approach that better suits the reality of a plant environment. We need a flexible kernel in combination with an appropriate calibration procedure. The second observation concerns the rate equations for growth, nucleation, and agglomeration. There appears to be some misconceptions, especially regarding the definition and application of supersaturation. But first, agglomeration and its relationship with hydrodynamics. The science of turbulence in a tank. Andrei Kolmogorov was a scientist who made major contributions to the understanding and description of turbulence as follows. An agitator introduces kinetic energy into the fluid of a tank in the form of large eddies or a vortex. These break down into smaller eddies and even smaller eddies and so on, until all the kinetic energy has been converted into thermal energy as a result of viscous-induced shear. The breakdown proceeds through three categories of eddy sizes: large, full turbulent eddies, medium-sized eddies in a transition zone, and small laminar eddies. This looks similar to the classification of fluid flow through a pipe as a function of the Reynolds number. Except the Reynolds number is dimensionless, while this scale here is a microscale with a dimension of length, in our case expressed in microns. You go from fully turbulent to fully laminar, from primarily inertia effects to primarily viscosity effects, from no energy dissipation to complete energy dissipation. The microscale where viscosity starts to play a role and energy dissipation starts is the so-called Taylor microscale. The transition point from turbulent to laminar is the so-called Kolmogorov microscale. How does this translate into particle interactions and agglomeration? In the process of agglomeration, there are two steps: collision and consolidation. First, collision. Particles smaller than the Kolmogorov microscale travel parallel to each other inside the small laminar eddies. In laminar flow, you will normally have a viscosity-related, shear-induced velocity gradient. Collisions between these small particles occur because particles catch up with each other as a result of this velocity gradient. The chance of collision as a function of particle size has been worked out mathematically by Smoluchowski and others. I'll show you in a moment. Particles larger than the Kolmogorov microscale are subject to trajectory changes and velocity changes relative to the fluid because of inertia effects. This is the main cause of collisions, and these collisions are with all particle sizes, thus also with small particles crossing their way. The second step is consolidation. This is the balance between cementation and rupture, thus between growth rate and shear rate, which is proportional to agitator power input. Regarding rupture, you can easily visualize that a doublet of a large particle with a small particle has a greater chance of survival than a doublet of two equal-sized particles. Doublets larger than the Taylor microscale do not survive the full turbulent forces. An agglomeration kernel has two elements: agglomeration rate, which depends on, for instance, growth rate, shear rate, temperature, and a size kernel describing the chance that a particle of size x forms an agglomerate with a particle of size y. Expressions exist for the Kolmogorov and Taylor microscales. You will find those in the paper. But because of the variety of hydrodynamic conditions within a precipitator, we won't use those expressions. Instead, we simply find the values for those microscales through calibration of a new and flexible size kernel, which has a laminar component and a turbulent component. The laminar component is taken from publications by René David, who studied some non-alumina hydrate-related agglomeration. The laminar kernel on Smoluchowski, with collisions being primarily the result of a viscosity shear-induced velocity gradient. The turbulent component is again taken from René David's publications. It consists of two terms. The first term describes the general particle interactions under turbulence. And you can see from the expression and the resulting graph that doublets of a large particle with a small particle have a greater chance of survival. The second term causes agglomeration to taper off when the agglomerate size approaches the Taylor microscale, above which agglomerates do not survive. The next step is combining both components. For this, we use a Rosen-Ramler type expression as the transition term from laminar to turbulent. Rosen-Ramler is often used to describe cumulative particle size distributions and to describe partition curves of hydrocyclones. The midpoint here is the Kolmogorov microscale. The alpha is the transition sharpness, which can range from steep to very gradual. Tested with planned data, the new kernel worked better than existing ones, so it is an improvement. But I was still not 100% happy with some of the results. Some refinement was needed. Dan Menche introduced some time ago in SysCAD the possibility of using a generalized mean of dx and dy multiplied by 2 as an alternative for just using dx plus dy for all kernels in SysCAD in general. Generalized means are a family of means whereby the outcome depends on the value of a parameter. Value 1 produces the straightforward arithmetic mean. Here I use parameter m for the laminar component and transition term, and parameter n for the turbulent component. This proved to be very useful because now you could enhance or temper the preference of small particles to agglomerate with large particles and extend agglomeration of small particles with large particles beyond the Taylor microscale. This slide shows the effect of using generalized mean in kernels in general. The first row shows graphs of the generalized mean multiplied by 2 for 3 values of parameter n. The middle row and the bottom row show how the generalized mean multiplied by 2 compares with the original straightforward dx plus dy. When parameter n equals 1, you get the normal arithmetic mean multiplied by 2, and nothing changes. You still end up with dx plus dy. The same applies when dx equals dy. But in all other cases, the further away parameter n is from 1, and the further away dx is from dy, the further away the generalized mean of dx and dy multiplied by 2 will be from dx plus dy. You can see that for values of parameter n smaller than 1, agglomeration of small particles with large particles would be reduced. And in the case of the new kernel, the preference of small particles to agglomerate with large particles is tempered. When we make this substitution for dx plus dy, we obtain the final kernel. In this example here, I used the value of 0.05 for parameter n, which is a typical value that I found through calibration. While agglomeration between small and large particles is tempered, such agglomeration still occurs well beyond the calibrated Taylor microscale of 78 micron. Thus, there is a dual effect. The final kernel has a large number of variables, which allows you to shape the kernel into the correct profile of particle interactions. At the same time, the kernel is still based on fundamental principles regarding the impact of hydrodynamics on agglomeration. This ends part 1 of the presentation. In part 2, we continue with calibration of the new kernel and with a discussion on rate equality.